So, in the last couple of lectures, we have been solving the high Peclian number transport past rigid surfaces, where the velocity field decreases to 0 at the surface. Okay. First, we solved for the heat transfer past a flat plate, which had a heated section, okay. And the velocity profile was fully developed, and it decreased to 0 at the surface. Okay. And the second case, we had solved for the heat transfer in a stagnation point flow. Okay. Okay. And in both cases, we had got the equation for the scale temperature T star, which is equal to TW T okay, if the wall temperature is Tw and the temperature far away is T infinity. Okay, we got this T star as a function of eta, which is equal to Z by delta x. Okay. In both cases, the equation for temperature in terms of delta x was minus eta square dt by d eta is equal to d square T by d eta square. The temperature T star was equal to that was the equation for the temperature. The heat flux Qz at z is equal to 0 was equal to k into Tw minus T infinity by delta x, okay, into 3 power 2 by 3 by gamma of 1/3. Okay. Or let me just recall for you what the expression was. Okay. Okay, so that was the expression, and this had the numerical value, okay, that this was equal to minus k into Tw minus T infinity by delta x 3 power 2 by 3 by gamma of 1 by 3. Okay, so that was the expression for the heat flux. Okay. Now, we will try to solve a different configuration, and that is for the heat transfer in a pipe, okay, which has a heated section here. Okay. Starting at this location x is equal to 0. So, this is the x coordinate, okay. This is the x coordinate, okay. This is the radial coordinate, okay. At the wall of the pipe, this is the x coordinate starting at the start of the heated section. And as you recall, for the flow in a pipe, a laminar flow, the velocity profile is a parabolic velocity profile. Okay. And when there is heating from the wall, you would expect the effect of the wall heating to be restricted to a thin region close to the wall. You would expect the heating from the wall to be restricted to a thin region of thickness delta x close to the wall. Okay. If delta x is much smaller than the radius of curvature of the pipe, you can consider the pipe to be locally flat, the surface of the pipe to be locally flat. Okay. If the thickness of the region, the boundary layer within which there is a temperature disturbance due to the heating at the wall, if that is much smaller than the radius r of the pipe, we will come back and examine the conditions under which that assumption is valid. So, if the thickness is much smaller than the radius of the pipe, you would expect the pipe to be in the same as the heat transfer from the surface of the pipe, from the wall of the pipe, to be the same as the heat transfer from a flat plate, okay, because the thickness of this region is much smaller than the radius of curvature. So, the curvature does not matter, okay, and you can consider it to be a flat plate. For a flat plate, we already have the correlation for the heat transfer. Okay. If you recall, for a flat plate, the heat transfer correlation was Q average is equal to K into T w minus T infinity, where T w is the wall of the pipe and T infinity is the temperature in the fluid, okay, far from the surface. When I say far from the surface, I mean that the distance from the surface is much larger than the boundary layer thickness, okay, which is the same as the temperature at the entrance. Okay. Okay, so, when the distance from the surface from the pipe wall is much larger than the boundary layer thickness, the temperature is equal to T infinity. Okay. So, we had it as K into T w minus T infinity into, there was a constant 0.81, okay, okay, divided by alpha L d by V s prime whole power 1/3. Okay. Okay. Where V s prime was a strain rate, which was equal to dVx by dz at z is equal to 0, if the coordinate z is the distance from the flat plate. Okay. If the coordinate z is the distance from the flat plate, that is basically the strain rate at the wall of the pipe. Okay. And this coefficient here came out of that 3 power 2/3 by gamma of 1/3, if you recall, okay, when we did it for the flow past a flat plate. So, we can simply use this in order to find out what is the correlation for a pipe flow. All we need to know is for what is the strain rate at the wall of the pipe. Okay. For the parabolic profile, the velocity was equal to 2 times V average into 1 minus r square by r square, as you recall. Okay. 2 times V average times 1 minus r square by r square. When expressed in terms of the diameter d, okay, d is equal to 2 times r, okay, or r is equal to d by 2. Okay. So, this will just be 2 V average into 1 minus 4 r square by d square. Okay. Okay, that is the expression for the velocity field. Okay. dVx by dr is equal to minus 16 r by d square. Okay. Just taking the derivative, I have missed out a factor of V average, I am sorry. Okay. And the strain rate at the surface dVx by dr at r is equal to d by 2 is going to be equal to 8 V average by d. Okay. Just substitute r is equal to d by 2 to get the strain rate at the wall. Okay. So, this is 8 times V average by d. If you recall, when we did the discussion of the pipe flow, we had got this as 4 times V average, I am sorry, yeah, 4 times V average by r, okay, or 8 times V average by the diameter. Okay. So, this I have to substitute into the expression for the average flux. Okay. So, Q average is equal to K, let me put the factor here, okay, into 8 V average by d square alpha L whole power 1/3. Okay. Just substituting 8 V average by d in this expression here. And the Nusselt number is defined on the basis of the pipe diameter. Okay. So, the Nusselt number is defined as Q average by K into T w minus T infinity by D, okay, defined using the length scale as the diameter of the pipe. Okay. So, this is equal to 0.81, okay, into D into 8 V average by alpha L D square whole power 1/3. I am sorry, there is no factor of D here. Okay, so this okay, it's just alpha L by V s prime. Okay. Okay, so this 8 power 1/3 is equal to 2. So, I will get a factor of 1.62 into V average D by alpha power 1/3 D by L power 1/3. Okay. Okay, so this okay, so this is the expression for the heat transfer for the Nusselt number as a function of the Peclet number, okay, in this particular case. Recall that the correlation that we had derived for the Nusselt number for a laminar flow earlier in this course, we had not derived it, we had just given you the expression that was 1.86 P e power 1/3 d by L power 1/3. 1.86 into P e power 1/3 d by L power 1/3. And from first principles we have derived the same correlation subject to a slight difference in the coefficient in front. Okay. There is a difference in the coefficient. This difference arises for two reasons. One is that in the entrance section of the pipe the flow is not quite parabolic. Okay. There is a development length over which the flow becomes parabolic, okay, as you go downstream. There is a development length at which the flow becomes parabolic. Okay. And therefore, in the entrance section of the pipe the flow is not quite parabolic, and because of that the coefficient is different. And the second reason for the difference is the curvature of the pipe. Okay. So, for these two reasons the coefficient is slightly different, but subject to the difference in the coefficient, okay, we have managed to get the same correlation, okay, the same dependence on Peclet number and the same dependence on d by L. Note that the Peclet number is usually written as the product of the Reynolds number and the Prandtl number. Okay. 86 R e power 1/3 P r power 1/3 d by L power 1/3. Okay. And usually there is an additional coefficient which is mu by mu w for okay, in order to take into account the effect of the variation in viscosity with temperature, where mu w is the fluid viscosity at the same temperature as the wall, and mu is the fluid viscosity at the same temperature as the bulk of the fluid. Okay. So, this coefficient we were not able to get using first principles, but the other functional dependence we managed to get exactly using this expression. Okay. So, okay. So, So, there was an assumption here, and that was that this boundary layer thickness delta x, delta x is much smaller than the radius of the pipe. Otherwise, the boundary layer from the two sides will merge. If delta x is comparable to the radius of the pipe, then we can no longer use the boundary layer approximation, because here we have assumed that the boundary layer thickness is much smaller than the radius of the pipe. Now, what is delta x? So, we had just written the expression for delta x here is equal to alpha L by V s prime whole power 1/3. It has to have dimensions of length. So, alpha has dimensions of length square per time times the length. So, there is length cubed by time per time, and V s prime is a strain rate, the derivative of the velocity with dimensions inverse time. So, dimensionally this is the boundary layer thickness with the factor C delta set equal to 1 in that calculation for the flow past a flat plate. And we have an expression for V s prime. So, this is equal to alpha L by V s prime, recall, is equal to 8 V average by D. So, this is equal to alpha L D by V average power 1/3 into 1 by 2. Because 8 power 1/3 is just 2. So, the ratio, I have missed a factor of 3 here. So, the boundary layer thickness, there is a factor of 3 alpha x by. No, this is correct, alpha L. In the boundary layer thickness, I have missed a factor of 3. Kindly go back and check the calculation that we had done for the boundary layer thickness. There was factor of 3 in the boundary layer thickness because of that factor of 3 that was there in the expression for the boundary layer thickness in terms of the expression for the similarity variable. There was a coefficient that had to be equal to 1, and that had a factor of 3 there. So, the boundary layer thickness, this is an order 1 factor. So, you do not strictly need to incorporate it, but since we had written the factor of 3 there, I will continue with that factor of 3. So, this is the boundary layer thickness. The ratio delta x by d by 2, boundary layer thickness and the radius is equal to 3 alpha L by V average d square whole power 1/3. So, this is the expression for the ratio of the boundary layer thickness and the radius of the pipe. So, this is the expression. Our calculation is valid only when this is small compared to 1. So, 3 by P e L by d whole power 1/3 is small compared to 1. Which implies that L by d is much smaller than P e by 3. And boundary layer thickness is comparable to L for L by d is approximately equal to P e by 3. So, this is the limitation of the analysis. recall that when we started doing the analysis, the assumption was that the boundary layer thickness is small compared to the radius. Only then could we use the same expression for the heat flux from the surface as we had for the flow past a flat plate. Okay. That expression could be used only when the thickness is much smaller than the radius of the pipe, so that you can consider it as a flow past a flat plate, and so that the two the regions where there is a disturbance due to the temperature field due to the heating on all sides, right, they will merge when the boundary layer thickness is comparable to the radius of the pipe, and the analysis is no longer valid. So, that is the reason that in correlations you will see that this correlation, okay, this correlation of this kind, okay, is valid only when the length to diameter ratio is less than a maximum value, okay, and that maximum value is comparable to the Peclet number itself, okay, in the limit of high Peclet number. In that case, we can calculate the average flux from the wall just based upon the assumption that the boundary layer is much thinner than the radius of the pipe, and therefore, we can consider this as the same as the flow past a flat plate, where there is no length scale, and therefore, the only length scale is obtained by a balance between convection and diffusion, that is the boundary layer thickness. So, let us consider for a practical example, okay, what is the length by diameter ratio at which the boundary layer thickness becomes comparable to the pipe diameter. Okay. So, consider the flow with average velocity V average is equal to 2 centimeters per second in a pipe with diameter is equal to 1 centimeter, okay, of water with, okay, thermal diffusivity. (1.5 into 10 power minus 7 meters square per second). Okay. Up to what length of pipe can we at what length of pipe does the boundary layer thickness calculated in this way become comparable to the radius of the pipe, okay, at what up to what length of pipe. Okay. So, for this we can easily calculate the Peclet number, okay, is equal to V average d by alpha. Okay. V average is 2 into 10 power minus 2, okay, into, okay, meter per second into 1 into 10 power minus 2 meter divided by 1.5 into 10 power minus 7, okay, meter square per second. See, okay. And if you calculate this, okay, there is a 10 power minus 7 in the denominator. So, if you calculate this, you will get 1.33 into 10 power 3, okay, which means that L by D has to be approximately 1.33 into 10 power 3 by 3, okay, which is 4.44 into 10 power 2. Okay. So, this is the length at which the boundary layer thickness becomes comparable to the pipe diameter. Okay. Okay. Thus the pipe diameter and the boundary layer thickness, I am sorry, yeah. Okay. Now, okay, the pipe radius and the boundary layer thickness are comparable when L by D is comparable to PE by 3, or because the pipe yeah, I am sorry, yeah, okay. I had actually done the calculation for 1 centimeter per second and 2 centimeters. Okay. Okay, so, if the diameter is 2 centimeters and the average velocity is 1 centimeter a second, this means that length has to be approximately 8.9 meters, okay, is equal to 4.44 into 10 power 2, okay, into 2 into 10 power minus 2 meters per second, okay, in this particular example. Okay. My apologies, I had interchanged the average velocity and the diameter when I first stated the problem. Okay. So, you need a pipe of length 8.9 meters if the pipe diameter is 2 centimeters. Okay. You need a pipe of length 8.9 meters before the boundary layer thickness becomes comparable to the pipe radius. Okay. And then the boundary layer approximation is no longer valid. Okay. If your pipe diameter is much less than 8.9 meters, almost 10 meters, you can consider the boundary layer thickness to be much smaller than the pipe radius, and therefore, use the same expression that we had. Okay, assume that it is conduction into an infinite medium, because the boundary layer thickness is much smaller than the characteristic dimension, and use the correlation for the flow past a flat plate. Express the strain rate in terms of the strain rate at the wall in terms of the average velocity and the diameter. Okay, express the strain rate at the wall in terms of the average velocity and the diameter, and use that in order to calculate the correlation for the Nusselt number as a function of the Peclet number. Okay. And we get the same expression for the Nusselt number, except that this constant is slightly different. Okay, except that this constant is slightly different. The functional dependence of the Nusselt number on the Peclet number turns out to be identical to what we had for the case of for the correlation that is commonly used for pipe flows. Okay. The dependence on the Peclet number and the dependence on ratio of diameter and length, those are exactly the same. The constant is slightly different in this case. Okay. So, that is the only difference. Okay. And this you can do for any type of pipe of flow in a pipe. Okay. So, for example, if you recall, we had solved earlier the power law, the flow of a power law fluid in a pipe. Okay. Earlier we had solved the example of the flow of a power law fluid in a pipe. Okay. Where the constitutive relation was given by tau x r is equal to mu into dVx by dr into dVx by dr power n minus 1. This was not mu, but it was kappa. Okay. N is the power law index, and kappa is the flow consistency index. Okay. And for that we had got the average velocity as minus 1 by 2 k dp by dx power 1 by n. Note that dp by dx was negative in this case. Okay. You can go back and refer to that, into n by n plus 1, okay, into r power n plus 1 by n. Okay. And if I express r in terms of d by 2, okay, I will get minus 1 by 2 k That was the expression for the average velocity, and the strain rate at the wall was that dVx by dr at r is equal to r. Okay. This was equal to minus 1 by 2 k dp by dx whole power 1 by n, okay, into r power 1 by n. Okay. Okay. And now you can get the boundary layer thickness as delta x is equal to 3 alpha x by Vx prime, okay, by dVx by dr. Okay. Okay. and you can express dVx by dr in terms of the average velocity. Okay. You can express dVx by dr in terms of the average velocity, because both of these are proportional to this common factor. Okay. So, we can express dVx by dr in terms of the average velocity, and you will get this as 3 alpha n x d by 2 into 3 n plus 1. Okay. Should be 3 n plus 1, my apologies. Okay. Okay. You can express it as 2 into 3 n plus 1 V average by n d. Okay. And substituting this into the expression, okay, Q average is equal to 0.181 k into T w minus T naught, okay, divided by alpha L by V s prime whole power 1/3. Okay. The modification of the expression for the flux will be 0.81 P e power 1/3, okay, into 2 into 3 n plus 1 by n whole power 1/3. Okay. So, this is the simple extension for the flow of a power law fluid. Okay. The only thing that we need to modify is the expression for the average velocity in terms of the pressure gradient, strain rate in terms of the pressure gradient. From these two, determine what is the expression for the strain rate in terms of the average velocity. Okay. Substitute that expression for the strain rate in the same expression for the heat flux and for the Nusselt number correlation, okay, and you will straight away get what is the correlation for the Nusselt number. Okay. So, this Nusselt number is equal to Q average by K into T w minus T infinity by d. Okay. And if you substitute these expressions, I will not go through the details, what you will get is 0.81 P e power 1/3, okay, into 2 into 3 n plus 1 by n power 1/3 into d by L power 1/3. So, this is the simple extension of the same analysis for a pipe flow to a power law fluid. Okay. The only thing that changes is the relation between the average velocity and the strain rate, okay, because the relation between the average velocity and the pressure gradient changes, the relation between the strain rate and the pressure gradient changes, and therefore, when we express the average velocity in terms of the strain rate, you get a different coefficient here, okay, and that coefficient appears in the final expression. And you can easily verify for n is equal to 1, the coefficient is 8, as we had for a Newtonian fluid in a pipe. So, this explains how we get correlations for a pipe flow, okay, for the flow in a pipe, just using the boundary layer analysis and the assumption that the thickness of the boundary layer is much smaller than the pipe radius. I will continue this for other shapes such as flow past a spherical object in the next lecture. I will see you then.